NASA making a historic announcement today that the Voyager probe has entered interstellar space, that place between the stars. It's now...
Since 1977, Voyager 1 has been exploring space, going beyond than anyone could have ever dreamed. This ancient spacecraft, which was first built to research Jupiter and Saturn, has already ventured into interstellar space and is still returning enigmatic data from uncharted territory. However, what is it actually like to be out there? Is space more dynamic and living than we think? Most importantly, did we step over a boundary that we weren't supposed to? Voyager 1's historic launch and primary objectives. Many people consider Voyager 1 to be one of the greatest feats of human deep space exploration. It was built for a spectacular tour of the outer planets, namely Jupiter and Saturn, and was launched on September 5, 1977. People did not realize at the time how far this little spacecraft would travel or how many decades it would continue to operate. Voyager 1 provides us with a look into the extreme regions of our solar system and beyond, and is now acknowledged as the furthest man-made object from Earth. NASA was eager to capitalize on a unique outer planet alignment that only happens once every 175 years in the 1970s. A spacecraft passing these planets could use gravitational assistance thanks to this alignment, burning a planet's gravitational pull to change course and increase speed without burning a lot of fuel is known as a gravity assist. An ambitious mission could use this method to visit several distant planets in a single journey. Participating in this mission profile were Voyager 1 and its twin, Voyager 2, which launched on August 20, 1977. The primary goal of the expedition was to explore Saturn and Jupiter. Their atmospheres, moons, rings, and surrounding space environment were all of interest to scientists. Prior to Voyager, telescopes, which aren't always able to see fine detail, were the main source of our knowledge about these far-off worlds. Everyone was shocked when the spacecraft passed Jupiter in 1979 and revealed active volcanoes on the moon Io. New information regarding Jupiter's weak ring system and swirling clouds in its atmosphere. Following Jupiter, Voyager 1 proceeded to Saturn in the early 1980s, revealing previously unobserved features and new moonlets, as well as our first up-close views of Saturn's intricate rings. Scientists decided to launch Voyager 1 beyond the orbits of Uranus and Neptune, and eventually beyond Pluto's path after it had accomplished these important mission tasks. Voyager 1 was powered by a radioisotope thermoelectric generator, or RTG, which allowed it to continue transmitting data. Instruments were eventually switched off to save power, yet there was still enough capability to continue taking useful measurements. The spacecraft outlasted many projections, sending data long after its original mission concluded, despite mission designers' expectations that its power and systems might only endure until the late 1980s or early 1990s. NASA's Jet Propulsion Laboratory, or JPL, in Pasadena, California, provided expert direction and meticulous engineering, which contributed to this achievement. These spacecraft have evolved into long-term research instruments for comprehending the heliosphere and interstellar space, yet engineers still frequently view them as time capsules containing the golden record for future discoverers. Voyager 1 is still sending signals that help scientists better grasp the boundary between our solar system and the deep unknown, despite the fact that several of its equipment are no longer in use. A chaotic area of charged particles and cosmic rays is produced at this boundary when the solar wind and the interstellar medium encounter. The protective function of the heliosphere. The heliosphere is one of the most crucial ideas when discussing Voyager 1. To put it simply, the solar wind dominates the heliosphere, which is a bubble-like region of space, a constant influx of charged particles from the sun, mostly protons and electrons. This bubble serves as a kind of protection against specific kinds of cosmic radiation and stretches well beyond the orbit of the outer planets. Particle flows, magnetic fields, and local space weather are all shaped by the sun's powerful effect inside this bubble. The heliosheath, the termination shock, and the heliosphere itself are important regions. The solar wind suddenly slows down during the termination shock when it starts to crash with the interstellar medium, which is the region outside our solar system that is packed with gas, dust, and cosmic rays. The spacecraft enters the heliosheath, a turbulent region where the solar wind is slower and more chaotic after overcoming the termination shock. Last but not least is the heliosphere, which is frequently regarded as the heliosphere's outer border or boundary, where the forces of interstellar space and the solar wind are roughly balanced. Many individuals believed that these borders were smooth, or at least predictable prior to Voyager 1. A straightforward passage from the solar wind zone to the interstellar region was proposed by a number of models. Voyager 1 and Voyager 2 data, however, showed that these regions are more messier. Cosmic rays can enter the heliosphere through unexpected turbulence and hole punch zones created by interactions with interstellar magnetic fields and plasma. The area close to the heliosphere may occasionally be further disturbed by solar events such as coronal mass ejections that radiate outward. Protecting Earth against galactic cosmic rays, which are charged particles that travel across galaxies at almost the speed of light, is another function of the heliosphere. Both spacecraft electronics and astronauts may be at risk from these cosmic rays. Scientists can more accurately forecast when cosmic rays will be more or less intense by examining how the heliosphere evolves over time. For instance, the stronger solar wind can assist protect the solar system from some cosmic rays during times of high solar activity. Deeper penetration of high-energy cosmic rays may occur during times of low solar activity. Voyager 1 has traversed these areas for decades, collecting data that was previously unavailable to mankind. Its data assisted in confirming that the termination shock could fluctuate based on the sun's activity and other circumstances rather than being positioned at a set distance from the solar. Additionally, it demonstrated that the heliosheath was more intricate than previously believed, containing a mixture of magnetic fields, heated plasma, and whirling flows coming from many directions. A genuine spacecraft was suddenly prodding this area, which had previously only been anticipated theoretically, and sending back signals. Knowing the heliosphere entails knowing not just the environment of our own solar system, but also that of other Milky Way stars. A heliosphere powered by stellar winds is probably present in many stars. Scientists can make educated guesses about the behavior of the border areas surrounding other stars by closely examining ours. Because the amount of cosmic radiation a planet receives can affect whether life could exist on its surface, this has broad implications for research on exoplanets as well. Thus, Voyager 1's investigation of the outer reaches of the heliosphere contributes to more general inquiries concerning habitability and extraterrestrial life. Going across interstellar space. Voyager 1 made headlines on August 25, 2012, when it formally entered interstellar space by passing what scientists refer to as the helop. Following a thorough analysis of particle count data, magnetic field measurements, and abrupt decreases in heliospheric particle concentrations, scientists made this revelation. It was more complicated than just crossing a line on a map. Rather, it included a detailed examination of the changes in magnetic field orientations and cosmic ray intensities around the spacecraft. By measuring the local electron density, scientists can verify an interstellar crossing. Compared to the heliosphere, interstellar space has a higher electron density. Therefore, a sharp increase in electron density detected by Voyager 1 indicated that the spacecraft had entered a new environment. The way cosmic rays from beyond the solar system behaved was another hint. Cosmic rays are slowed or partially deflected inside the heliosphere. Thus, the increase in cosmic ray counts suggested that Voyager 1 had left the protective bubble of the Sun. The road is far from over, though, even after reaching that milestone. The barrier may not be an all-or-nothing occurrence, according to others. Alternatively, the spacecraft might go via filaments or fingers where heliospheric plasma and interstellar particles mix, allowing for a slow back-and-forth crossing. Different lines of evidence, Variations in plasma wave oscillations, changes in the direction of the magnetic field, and variations in charged particles are all part of the controversy around the exact moment Voyager 1 departed the heliosphere. However, there is ultimately agreement that the spacecraft is in fact in interstellar space, which indicates that it has left the primary area of the Sun's impact. Voyager 1 has not completely escaped the gravitational pull of the Sun, even though it is in interstellar space. To be totally free of our star would actually require a far greater distance. But crossing the helop is a first from the standpoint of space physics. It implies that researchers may now directly examine the local interstellar medium, which is the gas and dust-based substance that exists between stars and has the potential to create new stars and planetary systems in the future. One surprising finding is that as Voyager 1 entered interstellar space, the direction of the magnetic field around it didn't shift as sharply as anticipated. This implies that the border region is more permeable than expected, or that the lines of the magnetic field from the enigmatic field from the Sun may be somehow aligned with the interstellar magnetic field. Data from Voyager 1 has demonstrated that a complete switch to an external field is not always required when entering interstellar space. Rather, the field of the Sun may be stretched or curved around the area Voyager 1 is traversing. Additionally, Voyager 1 captured what are called tsunami waves, shock waves that the spacecraft can detect as coronal mass ejections from the Sun travel outward and strike the interstellar plasma. These occurrences demonstrate how our star still influences local conditions, even outside the heliosphere. According to some scientists, the helipore is a leaky boundary that allows fields, plasma, and energy to continue interacting. Our understanding of this outer region becomes more complex as more evidence becomes available. It turns out that the spacecraft is not totally isolated from the Sun's impact just because it is in interstellar space. Rather, it is an area where the extended solar environment and the local galactic environment interact. NASA's communication and deep space network issues. We must examine NASA's Deep Space Network, DSN, to comprehend how we communicate with Voyager 1. The DSN is a global network of massive antennas dispersed over 3 key sites: Tidbilla near Canberra, Australia, Robo de Chavela near Madrid, Spain, and Goldstone in California, USA. Because at least one station can observe a specific spacecraft anywhere, it may be in the sky. This spacing enables continuous coverage of spacecraft regardless of which way Earth is turning. There are several different sized dishes in each antenna complex. The largest ones have a diameter of up to 70 meters, which aids in capturing the weak signals from distant probes such as Voyager 1. By the time Voyager 1 signals reach Earth, they are quite feeble. The signal strength can actually be much lower than a whisper. Sensitive electronics are used by the DSN to identify and decode these signals, turning them into ones and zeros that may be transformed into visuals and scientific data. The lengthy communication lag is one of the main obstacles. At distances of more than 150 astronomical units, it can take more than 20 hours for a signal to travel one way, even though Voyager 1's radio waves travel at the speed of light. As a result, two-way communication can easily surpass 40 hours. Scientists and engineers must therefore exercise patience. The spacecraft cannot be joysticked in real time. Rather, they have to plan commands far in advance and then watch to see if the probe reacts as they anticipate. It's also important to note that Voyager 1 systems are getting older. The spacecraft uses plutonium-238 fueled RTGs, and each year its total power output significantly declines. NASA must therefore carefully consider which instruments will continue to run. Additionally, problems may arise in subsystems like the attitude control system, which controls the spacecraft's orientation, or the flight data system. Sending orders, waiting for responses, and troubleshooting issues can take months when anything breaks. Additionally, NASA has to divide up DSN time across numerous projects. The DSN supports dozens of ongoing projects, such as probes investigating the Sun, satellites orbiting other planets, and rovers on Mars. Priorities must be balanced when scheduling to ensure that each mission has adequate antenna time. Even though Voyager 1 is no longer a main mission for planetary encounters, it still needs assistance in order to gather and send data on the interstellar medium. Operators may shuffle DSN time in order to get in touch right away if an issue occurs. All things considered, the DSN is essential to practically every deep space mission the agency does, not just Voyager 1. It is an essential component of the system that enables humans to communicate with the solar system's outermost regions and beyond, with multinational partners working together to keep our space missions on course. It also demonstrates the global aspect of space exploration, abnormalities and bugs in the data system. Minor issues can escalate into serious issues since Voyager 1 is beyond repair. Every issue, from sensor failures to stored memory problems, has the potential to impede or complicate data flow. Engineers discovered that Voyager 1 began transmitting jumbled data from its flight data system in the middle to end of 2024. It was initially difficult to diagnose because the cause might have been anything from a hardware malfunction brought on by decades of cosmic ray exposure to a straightforward software glitch. After months of trial and error, careful analysis of fragmentary data, and directives transmitted through the DSN, NASA eventually regained some degree of control. As soon as the data started to make sense, they recognized that the spacecraft's surroundings had altered. The measurements indicated that the outer edge of our solar system was experiencing greater turbulence than anticipated. Certain signals suggested that Voyager 1 might be subject to unknown forces or local disruptions, and the plasma environment appeared to be oscillating. The Plasma Wave System, PWS, which can identify oscillations in the charged particle environment, is a crucial tool for comprehending these anomalies. Scientists can determine particle density and activity by listening to plasma waves. For example, when the spacecraft meets shock waves from solar outbursts or crosses particular boundaries, the device can detect spikes in electron density. Restoring these signals was of utmost importance because the flight data issue threatened to obscure them. Additionally, the magnetometer's mag values are quite important. They monitor the strength and direction of the local magnetic field. A large-scale routing of magnetic field lines is one example of an unusual phenomenon that the magnetometer may observe. The data from Voyager 1 in late 2024 and early 2025 appeared to point to sudden changes, suggesting that the environment was not the quiet area that many models had projected. Rather, it resembled a whirling transition zone with abruptly moving pockets of charged particles. Detectors of cosmic rays also monitored high-energy particles from beyond the solar system. If the spacecraft is traveling through areas where magnetic fields are blocking or funneling charged particles, it can be determined by abrupt reductions or spikes in the cosmic ray count. Interpreting these findings was initially challenging due to the irregularities in the data. It was unclear whether the alterations were due to the spacecraft's instruments malfunctioning or a genuine change in the surroundings. Following the partial restoration of the flight data system, engineers were able to verify that the region was dynamic by comparing signals from other systems. The enigmatic signal at low frequencies. A consistent low-frequency hum at about 3 kHz is one of the most peculiar discoveries linked to Voyager 1 in recent years. This hum is located below the usual frequencies of plasma waves. The signal was initially written off as background noise, but as Voyager 1 advanced deeper into interstellar space, it became more apparent. There are various theories among scientists as to the origin of a 3 kHz tone. One explanation is that the spacecraft surrounding plasma has a natural resonance. An alternative theory is that the signal is generated by charged particles orbiting the Sun along magnetic field lines, but the regularity of this hum is what makes it so unusually fascinating. Variations in density or spikes in solar activity can cause changes in plasma frequency. However, despite varying solar circumstances, this hum has remained remarkably constant. While the mainstream scientific community tends to favor natural explanations wherever possible, others have conjectured about non-natural beginnings. Without additional information, it is challenging to completely rule out the possibility that the signal is a planned transmission, even though there is no obvious evidence of an alien culture. The hum appears more like a continuous wave that originates from cosmic medium interactions. This hum's existence also connects to the more general subject of electron density and plasma waves. Following significant solar outbursts, Voyager 1 has captured plasma oscillations at higher frequencies. However, there appears to be less variation in the 3 kHz tone. It does not increase or decrease in time with significant changes in space weather. This consistency could indicate that the signal is an interstellar medium drone. It could be a vibration caused by the interstellar magnetic field, background plasma, and cosmic rays interacting on a massive scale. According to several scholarly articles, this kind of steady wave could aid in more accurate measurements of local circumstances. The wave's frequency may serve as a baseline indicator of the density of the medium around Voyager 1 if it is correlated with the local plasma density. We may be able to compare signals in various near-interstellar space areas with the aid of future spacecraft or even the data from Voyager 2. It may be confirmed that hums are a common natural phenomenon if both spacecraft detect them at identical frequencies. A sustained low-frequency transmission could travel great distances since radio waves are good at traveling through space's vacuum. It might exist in numerous star systems if it is a universal background wave. It's interesting to consider whether sophisticated civilizations could recognize shifts in such basic patterns as a warning indication that something is approaching their borders. Even if that is highly conjectural, it emphasizes how any persistent, unexplained signal in space stimulates original thought on a variety of levels. The unfathomable powers and the pull of gravity. The sun, planets, dwarf planets, and big asteroids are among the known celestial bodies that are used to determine Voyager 1's official trajectory. There have been indications, nevertheless, that its course slightly departs from forecasts. Generally speaking, thermal phenomena, such heat from the spacecraft's RTG producing a modest propulsion, can account for these minor variances. Similar anomalies were seen by Pioneer 10 and Pioneer 11 previous probes, which were hotly contested before providing some partial natural answers. However, recent evidence points to an external pull that the known masses surrounding Voyager 1 cannot account for. Scientists have thought about dark matter clumps or rogue planets as potential culprits that may move through the galaxy without being seen. Another theory is that there might be a dense object or a tiny black hole out there, but the chances are slim. Astronomers search for gravitational lensing effects or minute variations in star positions to validate such a suspicion. However, there is currently no compelling evidence that Voyager 1 is being pulled by a compact, huge object. Some people also attribute unexplained gravitational behavior to dark matter. Although it is believed to comprise the majority of the universe's mass, it does not normally interact with light. There might be a slight gravitational pull if there was a dark matter cloud. However, according to the majority of dark matter models, it is dispersed somewhat uniformly throughout the galactic scale rather than in large, distinct clusters that would drag a spaceship down. Furthermore, other astronomical observations would have probably revealed local inhomogeneities on dark matter. What is causing the little drift, then? It's probably still a minor influence of the heat from the spacecraft or tiny thruster firing misalignments. The narrative is still intriguing, though, because it serves as a reminder that we do not yet fully comprehend all of the variables that could affect an object in deep space. Small alterations can even be brought about by electromagnetic forces. The spacecraft may experience difficult-to-detect momentum gains or losses if it picks up tiny electric charges or passes through an unanticipated plasma area. The official trajectory is still broadly in line with projections, according to most scientists, notwithstanding the enthusiasm around invisible forces. The challenge of measuring an object so far away limits the margin of error. The signals are quite weak, and each set of data must be carefully analyzed. Small inaccuracies could accumulate over time when the DSN tracks the craft's velocity using Doppler shifting techniques. Therefore, even though gravitational anomalies make for interesting headlines, The most straightforward explanation is typically that the spacecraft or minor measurement errors are to blame. Rumors of secrecy have frequently accompanied space travel due to both public curiosity and government concealment. Some people believe that information may be kept secret for security concerns whenever interesting data surfaces. The majority of NASA's scientific data is actually publicly available. Raw photos and instrument readings from missions such as Voyager, Cassini, and the Mars rovers are available for download from some archives. It is true, nevertheless, that not all data is immediately made available to the public. Although there are real precedents for increased secrecy in space research, NASA may withhold some conclusions until they are confirmed or until scientists have had time to write official articles. Some early flights, for instance, served both military and scientific purposes during the Cold War. As a result, the data release was occasionally incomplete. Coordination with government agencies is still possible in the current era if a discovery includes new technology or may have national security ramifications. Heavy secrecy is unlikely to be at work for Voyager 1, which is located far from Earth and not close enough to any planet to disclose new strategic details. It's more likely that NASA is hesitant to release data that is unclear or insufficient when an instrument malfunction occurs. However, the uncertainty might pique people's interest. The slow release of official pronouncements or the appearance of sensitive material can lead to speculation about secret signals or alien contact. Some believed that NASA had concealed evidence of a massive body hiding beyond the helop or of a manufactured signal with Voyager 1. However, scientists consistently offer more believable, everyday explanations. The scientific community provides input as new data is analyzed in peer-reviewed publications. The notion that space might not be empty frequently interacts with the public's curiosity with possible cosmic watchers or edges that fight back. Because it encourages greater interest in astronomy and astrophysics, the curiosity is beneficial. Although some of the conjecture may be exaggerated, it highlights how people inherently question whether we are alone in the universe or whether there is another being in our immediate vicinity. The wider cosmic landscape and its unexpected aspects. The Milky Way galaxy is full of gas, dust, radiation, and innumerable stars, all of which must be understood in order to fully appreciate the discoveries made by Voyager 1. There is more to interstellar space than nothing. In addition to evidence of heavier elements, it has an extremely low density of hydrogen and helium. The distribution of magnetic fields and plasma can produce large-scale structures that we are just now mapping, and temperatures can fluctuate greatly. The galaxy may be shaken by supernova shock waves, which compress gas pockets into denser clouds that may eventually develop into star nurseries. This is also where the idea of cosmic rays fits in. These are high-energy particles from black hole accretion disks, pulsars, exploding stars, and other energetic settings that move close to the speed of light. Fewer of these rays enter the heliosphere because the sun pushes back against some of them through the solar wind. The boundary zone is important to scientists because of this. What cosmic radiation enters through our cosmic front door is filtered. Even though Voyager 1's instruments were created decades ago, they are still able to identify intriguing phenomena, including abrupt increases in the number of cosmic rays, variations in the density of local plasma, and changes in the magnetic field. Extreme solar outbursts have the potential to produce shock waves that eventually reach the spacecraft after radiating outward for months or years. We can learn how far the sun's reach extends and how cosmic weather can affect a boundary region long after the solar event has passed at Earth by seeing how these waves interact with the interstellar environment. The implications of this for prospective future cloud objects are likewise attracting increasing attention. Up to 100,000 astronomical units from the Sun, the Oort cloud is a fictitious shell made up of frozen comets that surrounds our solar system. If it can escape at all, Voyager 1 won't be able to do so anytime soon because it is still far inside that area. We may be able to predict how comets in the outer solar system are prodded into new orbits, occasionally causing them to move toward the inner solar system, by learning about the surrounding environment. In addition, astronomers can improve their star formation models by researching the interstellar medium. Interstellar gas clouds undergo a variety of chemical reactions. The formation, disintegration, and reconstruction of molecules creates the conditions for the eventual ignition of new stars. Scientists can gain an understanding of the processes that may be occurring throughout the galaxy by tasting a tiny sample of the medium at the frontier of our solar system. Thanks for watching another episode. Please like and subscribe for similar content.